Hello again. So let us solve this question together. Let's start by finding the rotor speed. So the rotor speed in RPM, in order to calculate it, we will need to first find the synchronous speed. And the synchronous speed can be found by knowing the number of poles and knowing the frequency of the source. So putting these values in the formula, we will get the synchronous speed as 1800 RPM. Now, once we have the synchronous speed, we can find the speed of the motor by the relationship between it and the synchronous speed through the slip. Notice that I have used the normal value of the slip without the percentage. And in this case, we got the rotor speed as 1780 RPM. So this is number 1 done. Next, in order to calculate the stator current, which is basically this current over here, we need to calculate first the equivalent impedance as seen from this terminal. So notice that these two components are in series and they are in parallel with those two. And then the result is in series with these two. So by doing so, we are able to calculate the total impedance. So you can go through the steps on your own and let me know if you didn't understand anything. So over here we are just taking the parallel values of the magnetizing reactance with Z2, which has been calculated over here. That is R2 over S plus JX2. And then finally, putting it in series, we're adding it with the impedance of the stator, we are going to get the magnitude and the phase of the impedance, which is seen at the stator. So in this case, in order to calculate the stator current, we have the per phase voltage, and we have now the total impedance. We plug them into this formula, and we get the magnitude of the current as well as its phase. We can see that it is lagging the voltage by 33.6 degrees. Now the next step is to calculate the mechanical power, which is given by this formula, and it is related to the power that has crossed the air gap. This means that we need to calculate the power that has crossed the air gap first. So to do so, we need to calculate the power in the air gap, but since we don't have the rotor current, we can make use of the values that we have just obtained. So let us see. We have obtained the stator current. We can also find through this the power factor. And if we have these parameters, in fact, we can start by calculating the input power. So to summarize, first we find the power factor, which is cosine positive of the angle, and we will get this value. Then we can calculate the input power, which is given over here, plugging in the voltage. So notice that this is the total voltage, and in this case we need to apply the phase, the total input power. And we have the stator voltage, which is also the line voltage, and we have the power factor. Putting these parameters in the formula, we get the input power to the motor as this value in watts. Now, remember that, so first there is the input power, so this is the input power, and there are some losses in the stator before the power crosses the air gap. So if this is the air gap, so we want to find what is this power. Okay, this is their thing. So the power of the air gap is the input power minus these losses. And the losses happen here in the resistance of the stator. So to calculate the stator copper losses, we need to apply this formula. So this is the total power. That's why we multiply it by 3 for all of the 3 phases. We have I1, which is the stator current that we have just calculated. We have R1, which is the stator resistance. and therefore we can find the stator copper losses in watts. Having this value in hand, now we can subtract it from the input power in order to get the power that has crossed the air gap. Once we have this value, we can find the mechanical power since we already have the slip. So we can insert it here and then we can find the mechanical power in watts. The next value we need to calculate is the output power. In this case, since they told us in the question that ignore any losses in friction or windage, in this case the output power will be the same power as the shaft. So it will be the mechanical power minus the rotational power. So this is the power losses in the copper of the rotor, which were given in the question as 1100. So since we calculated already the power, the mechanical power, we subtract the rotational power loss and then we get the output power in watts. If we have this, then we can calculate the torque of the load. So this is the output torque, which is P out divided by the speed of the motor in radians per second. Now, the question is how to get this value. You can refer to the previous example that we have solved together to know how to calculate the speed in radians per second if you have the speed in RPM. So plug in the numbers, you will get the torque, and this completes the requirement in number 5. The last requirement is to calculate the efficiency. Now, in our example that we solved before, we have calculated the efficiency as P mechanical, which is the output, since there are no friction or windage losses, divided by the output power plus any losses. Okay? But the efficiency can be calculated in a different way as well. So the alternative method to calculate the efficiency is simply P out over P in. So you want to know how much percentage you are getting as an output power if your input power to the motor was P in. So again, we have P in and we have P out. We don't need actually to calculate the power losses. We already have enough values to calculate the efficiency. So once we put them in the formula, multiply by 100, we get the efficiency as 83.7%. And that completes the solution of the question. Well, now we do have an interesting question. Have you thought of how we got the values of the equivalent circuit? I mean, how did we get the parameters, the resistors, and the reactance values? That's what we will be seeing next. So in order to determine these values, the most common ways is to do two kinds of tests. The first one is called the no-load test, and the other one is called the lock rotor test conditions. So let's start with the first one. In the no-load test, it is like an open circuit test that we have done on the transformer. It gives information about the exciting current and rotational losses. The test is performed by applying a balanced rated voltage on the stator windings at the rated frequency. When I say rated, I mean the operational frequency and voltage. So when the load is operating. And the small power provided to the machine is due to core losses, friction, and winding losses. The machine in this case will rotate at almost a synchronous speed, and this makes the slip nearly zero. What can we obtain when we perform this no-load test? We can obtain the per-phase current, voltage, and the real power. And these values will allow us to calculate the core resistance RC and the magnetizing reactance XM, which are these components over here. On the other hand, the locked rotor test, in this case, we would short circuit this end as we do in a short circuit test in a transformer. This will provide us the information about leakage impedances and rotor resistance. And the rotor is at the standstill while low voltage is applied to the stator windings to circulate rated current. And since there is no rotations at this particular condition, the slip is equal to 1. During this test, we will also be able to measure the per-phase current, voltage, and real power values, and these values will enable us to calculate the values of the rotor resistance, the stator resistance, as well as the equivalent reactance. So this, and that. Let us see an example to understand the meaning of these tests better. Let's say that a no-load and a locked rotor test are performed on a 6-pole 3-phase star-connected induction motor with the results shown in Table 3 and Table 4, respectively. We need to calculate all the equivalent circuit components. Also, calculate the power factor at no load and locked load. So this is at. Note that power measurements are per phase power. So all of these values are per phase values. So as I mentioned previously, let's start with a no-load test. This will give us the values of RC and the magnetizing reactance. How can we do that? So from these results, from the no-load tests, we can find the iron core losses resistance by this formula. So this is the voltage per phase divided by the per phase power, which has been given in the table. So putting their values, we get the iron core resistance in ohm. Now next, in order to calculate the magnetizing reactance, we need the reactive power. So first we need to calculate the apparent power, and we use the per phase voltage and per phase current. We get this value in volt ampere, and then we can get the reactive power using this formula that you have seen before. We plug the values of the reactive and the real of the active and the real power, sorry, the apparent and the real power. We get the value of the reactive power. Once we have it, then we are ready to calculate the magnetizing reactance. This value is the phase voltage square divided by the reactive power. And we get the magnetizing reactance in ohm. The final thing to calculate is the power factor at no load. You simply divide the real power by the apparent power, and you get the power factor at no load. Now, in a similar manner, we will get the parameters of the equivalent circuit, the remaining parameters of the equivalent circuit, using the locked load test, or the locked rotor test, also we can call it this way. Notice that in the given parameters, we are given the stator resistance. How can we make use of that? That's what we will see. Now we know that the summation of the stator resistance and the rotor resistance is equal to the real power divided by the per phase current square. So we have the per phase power given in the table. If we divide it by the current square, we get this value. So we have the summation and we have one of the resistance. So now we can get the value of the rotor resistance by subtracting it from this value, subtracting RS from this value, and we get the rotor resistance as 0.381 ohm. Similarly, in order to get the equivalent reactance, we need first to get the reactive power. If we get the apparent power from the per phase and the voltage and current, we can apply this formula over here, and then we get its value. And if we divide it by the per phase current square, we get the value of the equivalent reactance. Similarly, as we did before, we can get the locked load power factor by dividing the real power or by the apparent power, and that would be the power factor in the locked load. So that's how we calculate the equivalent circuit parameters using the results of the two different tests.